So now we go on to numerical integration. As we had said earlier, numerical integration is nothing but finding the area under a curve. So in fact not just numerical integration, integration in general is finding the area under a curve. Okay. So let us say we have some curve f of x, okay, and we want to find the integral of f of x dx. Okay. So this integral of f of x dx is nothing but this particular area under the curve. Okay. So geometrically, what are the various ways to approximate that area? Okay. So geometrically the various ways to approximate the area under the curve is basically this particular interval we can split into many intervals, since the splitting up could usually is going to be our choice. We will split up into various equally spaced intervals and then find the area under the small part of the curve for each of these intervals. Okay. So let us say that the entire region I have split into various intervals and the smallest interval is now represented as this particular curve. Okay. So what I have done is, for this curve I have looked at the smallest interval and then I have zoomed in that particular smallest interval, and let me call this the smallest interval rather than going from A to B, let me call this going from say x1 to x2. Okay. And now I want to find out the integral going from x1 to x2 of f of x dx. Okay. So what I will do is I will find out integral from x1 to x2 f of x dx, x2 to x3, x3 to x4 and so on, starting with x1 equal to a and ending at xn equal to b. So that is the strategy that I will do. Okay. So now we zoom in into one particular interval and try to see what are the different ways. Okay. And the different areas that one can possibly think of is, you connect this particular horizontal line and the area under this yellow line is going to be one possible way of approximating that area under the curve. The other possible way of approximating the area under the curve is, take this particular line and complete the rectangle over here. So that is the purple area. Okay. So the first area is the yellow rectangle, the second area is the purple rectangle, okay, and the third area is you connect this point with a straight line, and the third is the area under the trapezoid. Okay. So based on this we have three different numerical approximation. The yellow numerical approximation is going to be Euler's backward method, okay, in which the integral I, we will write that equal to f of x1 multiplied by x2 minus x1. Okay. The length of this segment is x2 minus x1, the length of this segment is f of x1. So the integral I is going to be nothing but f of x1 multiplied by x2 minus x1. The Euler's forward method is going to be I equal to f of x2 multiplied by x2 minus x1. Okay. So this is f of x2 and this particular area for this rectangle is f of x2 multiplied by x2 minus x1. Okay. That is the Euler's forward method. And the third method that we talked about is called the trapezoidal rule. Okay. And in trapezoidal rule, I is going to be equal to the area under the trapezoid. The area under the trapezoid is if we remember from our basic geometry is nothing but this length multiplied by this length plus this length divided by 2. Okay. So the trapezoidal way is going to be b, that is the breadth multiplied by L1 plus L2 divided by 2, that is the area under a trapezoid. We will substitute those values over here. Breadth is nothing but x2 minus x1, okay, and we have this term half multiplied by f of x1 plus f of x2, right. It is half multiplied by breadth multiplied by first length plus the second length, okay, and that is going to be the trapezoidal rule. Okay. So based on the geometric interpretation, we have the Euler's backward method, Euler's forward method and the trapezoidal rules. These are the three different ways. These two methods are first order accurate in delta x. If we call this difference as delta x, or let us call this as using a simpler notation h, if we call this particular difference as h, the Euler's backward difference method is order h accurate, the forward difference method is also order h accurate, the trapezoidal rule is order of h squared accurate. Okay. So what we are actually going to do in the next lecture onwards is going to derive this trapezoidal rule. We will actually derive, so this is using the geometric method that we have derived trapezoidal rule, where we will derive the trapezoidal rule once again using three different methods in the next lecture, and then we will go on to higher order formulae. These particular formulae are clubbed under the name Newton-Cotes integration formulae. Okay. In the forward and backward Euler's, in the Euler's method, we use the function value only at one point and create a rectangle. In case of trapezoidal rule, we use the function value at 2 points and create a rectangle. We have higher order Newton-Cotes formulae where we will use 3 points, 4 points and so on and so forth in order to create a more accurate method. Okay. And so essentially what we are going to see in the next lecture is this, is let us say we have an arbitrary curve of this sort, okay, and we want to find an integral between a to b. Okay. One possible thing is to take this particular midpoint, which is a plus b by 2, okay, and of course one thing we can do is we can construct a trapezoid between the first 2 points and another trapezoid between the next 2 points and get the area under the curve. Other alternative is to connect these 3 points with a second order polynomial curve, and that second order polynomial curve is probably going to look like this, and so the area under the red curve can be obtained as a better approximation of the true area, and this particular red curve will be known as Simpson's 1/3 rule. Okay. If instead of 3 points we are going to join a third order curve to the 4 data points, we will get Simpson's 3/8 rule, and so on and so forth. We can go to higher order rules as well. Usually we do not go beyond the Simpson's 3/8 rule, and we will see why that particular thing happens, or that particular thing is what we do in the next lecture. Okay, and after that we are going to cover the overall derivations and the error analysis of all these methods. So that is going to be our strategy for the next lecture, while covering the numerical integration formulae. Okay, thank you, and I will see you in the lecture 3.